Okay, so we were looking at Landau-Ginsberg theory, and let me just step back a little. Yeah. So this is the action that we derived by doing successive coarse-graining approximations, which involved two important approximations. First one was to replace the lattice by continuum, and the second one involved replacing discrete values of dynamical variables by a continuous dynamical variable, which is a scalar field phi. And the potential term was motivated by studying the behavior of the order parameter, in particular in the Ising model behavior of the magnetization, whereas the kinetic term was derived by actually looking at the Hamiltonian J psi dot Hj with nearest neighbor interaction and converting that into a derivative term. Okay, and what we said last time was this action has various features. One of them was, of course, that you could add the coupling of the dynamical field with the external field. If you are thinking of Ising model, this would be a magnetic field. If you are thinking of some other quantities, then there will be appropriate external field which would affect the order parameter. Phi, of course, was the continuum version of what is called the order parameter in the statistical models. And this action is local. So this is one important aspect, and it was spatially uniform in the sense that there is no explicit dependence on spatial coordinate. The third feature was that it was polynomial in phi, and which is also part of the reason why it is local. If it was like, say, if it depends on inverse power of phi or something, it would have been kind of manifestation of the fact that the interaction is actually non-local, and the summed up behavior looks like the inverse power. Okay. The other feature, which was, of course, the defining feature from Landau's point of view, was that whatever model that you would want to write down should preserve the symmetries of the original model, because the entire idea was based on the symmetry principles, and Landau's claim was that the transitions between different phases happen because different phases have different kinds of symmetries, and the phase separation lines are indicators of the fact that the phases across the lines have different symmetries. And if you try to preserve the symmetries of the model, then it will tell as to why the symmetry changes, or why the ground state of a system chooses to preserve or not preserve the symmetry. Okay. The other thing that we mentioned was that the model did not have higher derivative terms. It involved only the first order derivative of phi with quadratic power of it, and involved only up to phi to the fourth term, and we ignored phi to the sixth, phi to the eighth term. And this is, of course, because we are working in 3 dimensions or higher. Had we been working in, say, 2 dimensions, that means 2 space and 1 time, then we could have kept phi to the sixth term, but ignored phi to the 8th onwards. And had we been working in 1 dimension, which is 1 space and 1 time, then we wouldn't be ignoring any of these. We'll probably keep all of them. Okay, so somehow there is a tacit assumption in the Landau-Ginsberg model that they are working in dimensions t greater than or equal to 3. But one knows as to how to do Landau-Ginsberg formulation in lower dimensions. So it's not like it is one is a totally different formulation. It's the same formulation that one could kind of adapt. Okay. And as I said that, like, if you have external fields, you can just add those to the Lagrangian as a linear coupling to the order parameter. Okay. Okay. Then we talked about the path integral behavior this thing, because we said that this action can be thought of as a Euclidean action of the quantum field theory, and one could think of the partition function as a path integral over all possible configurations of the scalar field. Integral over all possible configurations of the scalar field with the Euclidean action which was written down earlier. Okay, so that in that spirit, one could think of the entire statistical model as a Euclidean path integral for this system. Okay. So coming back to the Landau-Ginsberg model, we can now use the saddle point approximation of the Landau on the Landau-Ginsberg partition function, and try to derive certain quantities within that approximation. Okay. Now, of course, one can always improve on saddle point approximation by studying fluctuations around it, doing various different techniques like doing random phase approximations and a variety of things. So it is not that the saddle point is the end of the story, but at least saddle point tells you what are the extrema around which you would want to study fluctuations. Okay, so let's consider the order parameter phi to be given by some configuration phi m plus the fluctuation around that. Okay, later on we will not use delta phi, but we will use some var phi to denote fluctuation. It's kind of difficult to carry delta phi around when you want to write it down in, say, action functional and so on. But nevertheless, right now this fluctuation is just to kind of find out locate the saddle points of the action. So what we will do is we'll substitute phi is equal to this quantity in the action that we had, which was grad phi squared plus a times phi squared plus g by 2 times phi to the 4, and with the overall factor of half. Okay. And so you substitute this, and of course to leading order, that means to zeroth order in delta phi, you get the action determined by phi m, and then you have a fluctuation around that. Okay. So so now this fluctuation, of course, if you go back to the lattice model, could be kind of written as fluctuation of any one of the lattice points. Okay, so therefore, like this contribution of these fluctuations to the variation of the action comes from all n lattice points, and therefore this is actually proportional to n. Okay, so in n going to infinity limit, therefore you would have this quantity kind of contributing a term proportional to n. And remember, the Euclidean path integral action is either the minus s, like that. So you have a sm, s of phi m plus or rather minus delta s. But if delta s is proportional to capital N and capital N goes to infinity, then that term is exponentially suppressed and in fact just goes to 0. Okay, or rather. And therefore, what happens is that the main contribution really comes from the term S evaluated at phi m. Okay, so what we could do is that, like to first approximation, therefore we can kind of ignore the fluctuation around the minimum and just look at what is the minimum action. That itself would tell us the allow us to locate the extrema of the action. Okay, so that is something we know that corresponds to kind of deriving Euler-Lagrange equations. And So the Euler-Lagrange equations would be satisfied by phi m. I forgot to write the integral here. But S is the integral of the Lagrangian density, and equation of motion, Euler-Lagrange equations are these. Okay. So if we kind of ignore external magnetic field for the time being, this is just to kind of avoid getting inhomogeneous equation, but you could keep it if you want, if you don't worry about inhomogeneity in the equation of motion. But if you do that, then for this Lagrangian density, you would get the equation which would look like this. Okay, this is something you may have already done in quantum field theory. I don't know this thing, but this is a kind of straightforward variation of the Lagrangian density to get the equation of motion. Okay. Fine. So coming back to this term, remember this is a Euclidean action. So the Lagrangian density and Hamiltonian density are not very different because they are like, as you can see, all of them have same sign. So if you think about this as an energy functional, then you know that grad phi squared tells you that if your phi is spatially varying, see if phi is constant, then the derivative of phi is 0. So it's not going to cost you anything. But if phi is spatially varying its value at, if you look at it from lattice point of view, then from one lattice point to another lattice point, if the value of phi is changing, then the gradient of phi is of course non-zero, and it will contribute some non-zero value. And since this is gradient squared for a real scalar field, this quantity is positive definite. Okay, so therefore, spatially varying field would cost you extra energy. Okay, so therefore, if you are looking for something which is the lowest energy configuration, okay, and not look at configurations which are away from that, okay, so you are looking for what's called the equilibrium configuration, then you would want to set the gradient of phi to be equal to 0, so that you minimize the cost that you have to pay for fluctuation of the field and just concentrate on the absolute minimum value of the energy functional. Okay, so if you do that, then you just set gradient of phi equals 0, and if you set gradient of phi equals 0, then equation of motion would basically tell you that you set a phi plus g phi cube is equal to 0. Okay, and of course gradient of phi equals 0 also tells you that phi has to be constant, because otherwise the gradient wouldn't have vanished. Okay, so you are going to look for solutions which are constant, and they solve the right hand side of this equation is equal to 0 equation. Okay.
Sir?
Yes.
Would you go back to the expressions for A and G?
A and
G.
Oh, okay, yeah. Just a sec. Huh? Let us go back some distance actually. Yeah. So yeah. So we derived this expression from A and G from here. Oh gosh. Yeah. From here.
So here, both A and G, like they go as something like 1 minus Tc by T, or that inverse or something.
Not both. Only A.
I mean, G is also has a functional dependence on temperature, right?
It does, but it has a weaker dependence than this actually.
All right. My point was
Yeah.
that below T, yeah, so T less than Tc,
Yeah.
in that region, both A and G would be negative.
No, only A. G would involve squares of these quantities, so they won't flip sign.
G is always positive.
G is always positive, yeah, because if you expand this, then you will see that m to the fourth term would involve higher powers of T minus Tc. In fact, quadratic power
Yeah.
of t minus tc. So therefore, it wouldn't change sign even if t goes below tc.
Okay. No, my actual concern was that that might not be bounded from below the Hamiltonian that we might construct.
Yeah, yeah, I understand what you're saying. But what happens is that like only a flips sign, g doesn't. Okay,
Okay.
so that's why it doesn't go unbounded. But if you go to lower dimensions, like 1 plus 1, sorry, 2 plus 1 dimension, then there is a chance that g could flip sign. Okay, but then there exists a term which is like m to the phi. Okay, which whose coefficient doesn't flip sign. Okay, and that is why I was saying some time ago that we could have phi to the sixth term if you are in 2 plus 1 dimension. But if you are in 3 plus 1 and higher, you don't have those terms. And don't have in the sense they do not contribute. They are not responsible for determining dynamics of the theory. Okay,
Yeah. So
as
we
you
have
will.
some double well sort of a thing here.
Yes, this one will have double well. If you are in 2 plus 1 dimension, you can have triple well also. Okay, so
Okay.
we have a very important result coming out of this, namely from the double well. As we'll go ahead, we'll see it.
Okay.
Okay. Where were we? Yeah. So here. So we have to extremize the term which we could have called the variation of the potential energy term, and since we are not going to let kinetic energy cost anything to the energy functional, we just set this equal to 0. Okay, and this of course has three solutions. It's a cubic equation. One solution is of course phi is equal to phi m is equal to 0. Okay, that's kind of easy to see. The other solution is phi m is equal to plus or minus square root of minus a by g. Okay, so if you divide by phi, then you get this other solution. Okay, which is a quadratic equation involving phi m and a and g. Okay, so these are the two solutions. Now it may appear that we have only one real solution because we have a square root of minus a by g sitting around there. But that's not correct. Actually, that's kind of a bit misleading. And the reason why it is misleading is because the parameter a is written as a0 times t minus tc. That is the form that it takes. And for t greater than tc, this quantity is positive, and therefore this is a negative quantity inside the square root, and therefore these roots of this polynomial equation don't exist. They are complex roots. Okay, so there is only one real root. On the other hand, if t is less than tc, then a is negative. Okay, because t less than tc, this quantity is negative, and therefore a is negative. And because a is negative, phi m is a square root of a positive quantity because minus a is positive. Okay, and therefore below tc, all three roots are positive. Phi is equal to 0 is real. Phi m equals 0 is real, and phi m equals square root of minus a by g with plus minus sign, both are real. Okay, so therefore we end up getting three real solutions. Okay, now what we can do is we can like for example, like if you go back to the energy functional, maybe I don't want to roll back too much, but uh, yeah, let's stick around here itself. This term is actually a variation of the energy functional. So original energy functional was a by 2 phi squared plus g by 4 phi to the 4. Okay, if you ignore the kinetic term. And you know that these terms, phi to the 4 with g positive is going up because the potential is going to increase as phi m magnitude of phi m increases. Okay, so clearly, if you have a single solution phi m is equal to 0, which is the case for t greater than tc, you know that that is going to be the minimum of this potential. Okay, so we don't have to do too much work, but nevertheless, one could try to kind of just plug this answer into the energy functional and check what happens with it. Okay, so you can do this substitution. And you of course know that phi m would be the minimum of the potential when t is greater than Tc. Okay. On the other hand, if t is less than Tc, then when you substitute these as solutions, then what you find is that phi m is not a minimum, but it's a local maximum. Okay. That means the potential actually rolls downwards when you go away from phi is equal to 0. Okay. But it doesn't roll downwards indefinitely. It actually turns around and goes up again as the value of phi goes up. Okay. And the minimum value around which it turns around and goes up are the phi m is equal to plus or minus square root of minus a by g. Okay. So therefore, these are two degenerate minima, whereas phi m equals 0 is a maximum. So this is precisely the kind of double well problem that you may have done in quantum mechanics. Okay. The two states are degenerate is good for us. Why? Because although we have given um, continuous, I mean, we have kind of given a description in terms of continuous variable as an order parameter. Phi is a scalar field which can take any continuous value. Okay, the classical extremum of the energy functional actually has only two values. Okay, and this in Ising model would correspond to plus sign corresponds to all spin pointing up, then minus sign would correspond to all spin pointing down. And remember, Ising model has exactly two degenerate ground states, and these are those two degenerate ground states, their representation in the Landau-Ginsberg model. Okay, and you also know that SI going to minus SI was a symmetry of the Ising model when the external magnetic field is off. This problem is, of course, with external magnetic field is off because you don't have inhomogeneous term in the equation of motion, and you see that phi m going to minus phi m is actually a symmetry of the problem. Okay, so it takes one vacuum to another vacuum, which are related by signs. Phi m equals 0 was, of course, symmetric under phi m going to minus phi m. So therefore, the model actually preserves the symmetry that initial Ising model had. Okay, fine. So what we'll do now is compute critical exponents using the Landau-Ginsberg description of the system. Okay. So, but before that, any questions about this? So this is basically a problem of single well with quadratic and quartic potential with quadratic piece positive, quartic piece positive, that corresponds to t greater than Tc, and a double well potential when t is less than Tc, where quadratic piece is negative and quartic piece continues to be positive. Okay, that is how the potential is going to look like.
So,
Yes.
when we were solving this Lagrange equation,
Yeah.
in the partition function,
Yeah.
when we are calculating sort of the partition function, we say that the state corresponding to the minimum energy will contribute, and
Yes.
that's how we are sort of finding the solutions for this action term.
Yeah.
But that's only one-time minimization, and after we have gotten this equation, the
Yeah.
Lagrange equation, we should solve it for all the possible solutions. But we are kind
What
of
do you mean, all possible solutions?
we should also care about the solutions in which the gradient of phi is non-zero. That's the
Gradient.
point of showing that
Yeah,
those
but
solutions.
gradient of phi is not equal to 0 is not a minimum energy solution. No?
We could lower down the values of phi to make it low.
No, you cannot lower the value of phi below this. These are the lowest values of phi, or are the lowest values of energy. Excuse me, I didn't mean lowest value of phi.
We are minimizing twice.
Sorry?
We are minimizing the action two times. Once to find the minimum value of action, and
Yeah.
then again the minimum value of Lagrangian, sort of.
No, 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 no. See, I showed it in two steps, but you need not have to do it this way. You didn't have to kind of set it to 0 in this fashion. You could have just written down the entire equation, okay? And then you could have asked the question, what is the minimum energy solution corresponding to equation of motion, which is Laplacian acting on phi plus a phi plus g phi cube equals 0. Okay, and you will find that the answers, the lowest energy answers are these. Okay, what I did was I gave a physical motivation saying that, like, if you have a fluctuation uh, in the value of the field from one point to another point, that is the point when the gradient would be non-zero. That would contribute positive. That will always have a positive contribution to energy functional, and therefore, if you are looking for minimum, you should probably set this to the minimum value. But if you don't want to do it that way, you write down the entire equation of motion, okay, and ask what's the lowest energy configuration, and the answer is not different; it's still the same.
How does one figure out that exactly? Like here we have some physical motivation, but determining what would be the lowest energy configuration and stating that this is that. How does one
Yeah,
do that?
yeah. So in fact, like, it is often done this way, that you look at uh, you look at the energy functional. Okay, the the best way to do this is the following: that you write down energy functional for any field theory. Okay, then you manipulate that energy functional in such a way that you can write down that expression in terms of following quantities. Okay, one is that you can, I mean, it's not like everything can be written in this form. So therefore, you kind of divide the energy functional into possible parts. Okay, one part is like this, that you write that part as a total square. Okay, so your energy functional has, like, say, term a1, a2, a3, a4, a5. Okay, suppose. Then you may be able to write down say a1, a2, and a3, that set of terms, as, say, b1 plus b2 whole square. Okay, if you take b1 plus b2 whole square, then one term is a1, other term is a2, and the third term is a3. Okay, so you have taken care of a1, a2, a3, written that as b1 plus b2 whole square. Okay, then you have a4, a5 term. Okay, and then you can ask a question: what can you do with a4, a5? If you find that there is no way you can write that as a total square, then other thing that you could do is that whether you can check whether you can write down these terms as total derivative. Okay, fine. And if you cannot write down that as a total derivative also, or maybe one term you can write as total derivative and the other term survives, okay, then you have an energy functional which has the following form. One form is total square, then total derivative, and a term which cannot be written as either of these. Okay. Now the lowest energy configuration would mean that the total square should be 0, because it is always positive definite contribution, right? Positive semi-definite. So you set b1 plus b2 whole square to 0. Okay. Total derivative contribution total derivative term only has a boundary contribution. So you ask what is the field configuration that you want to choose at boundary. If your field configuration vanishes at boundary, then your total derivative term also does not contribute. Okay. Then your energy functional is minimized if the last non-total derivative, non-total square term takes the minimum value. Okay. So you get two equations. One is b1 plus b2 is equal to 0. So that b1 plus b2 whole square is also 0, therefore, and the last term is equal to is minimized. Okay, so this is the safest way of trying to locate the lowest energy configuration. Yes.
Here, when we are writing the action as some LDQ, LD4X, like
Yeah.
L being the Lagrangian density,
Yeah.
where are we exactly integrating? Like over the lattice, are we considering it to be infinite?
Yeah. We are considering now as an infinite space.
Then we cannot
Infinite
have a
continuous
phi
space.
equal constant configuration because energy will be infinite.
No. See, that is the point. That this phi is equal to 0, of course, will give you 0 energy. Okay, and
Yeah.
phi is equal to this quantity is the one which will give you finite energy configuration.
But this is integrated over d cube x, right, to get energy.
Yeah.
No, that will go to infinity because that is why we demand that physical fields die out at infinity, right? Like something like Klein-Gordon field or
Yeah.
Schrodinger field,
That is right.
they die
Yes.
out at infinity. That we cannot consider constant configurations, or else there will be some infinite energy
No.
solution.
So the point is this, that you get a potential okay, whose minimum lies at zero energy. Okay, is it okay?
I didn't get that one.
Okay, so what I'm trying to say is that the potential, since we are not doing theory of gravity, it is always possible for us to add or subtract constant quantities in the energy functionals. Okay, so what I'm trying to do is that I'm setting the minimum of the potential in such a way that the energy functional has zero value at this point. Okay.
I mean, uh, I just don't see why we are calling this a minimum energy solution.
I mean, I don't know how to explain. I mean, this is so you try doing this thing, right? I mean, you try writing down the energy functional in the form that I told you: total derivative plus total square plus the remaining piece, and then you try to keep the remaining piece to take lowest value. Okay. So what I'm trying to say is that it may give you an impression that phi is equal to constant quantity like this is integrated over the entire volume, gives you infinite energy, but that's not what is happening. What's happening is that this is the one which will give you zero energy. Okay.
I mean, it's fine for now. I think I don't know.
Yeah. So okay, let me put it a little differently. Let me take you back to quantum mechanics. Okay, it's the same issue in quantum mechanics. This thing. See, in quantum mechanics, like suppose we solve, say, hydrogen atom problem, and we say that the ground state energy is minus 13.6 electron volts. Okay. Now, in reality, that number could be anything actually. Only thing that we know is that the uh, energy difference between the ground state and the continuum is 13.6 electron volts. Okay, but you may have continuum starting at like energy minus 2 electron volts. Okay, if that is the case, then the ground state of a hydrogen atom would be minus 15.6 electron volts. To put it differently, only thing that we can actually measure are energy differences. Okay, as long as you are not doing theory of gravity. As soon as you put quantum theory of gravity, then everything is kind of I mean, all these statements are not going to hold, because gravity couples to absolute value of energy. But if you don't do theory of gravity like the way we are working right now, there is no gravity here. Then only thing that you know is energy differences. Okay, so therefore this configuration, I can just choose this configuration to have energy E equals 0. Okay, by just shifting the potential by overall constant. Okay, and that doesn't cost me anything. Okay, because all physical measurables would have that constant added on all sides. Okay, and therefore it just subtracts out. Okay, does that make sense?
I understood it's like setting an offset sort of a thing, but
okay, maybe we can revisit this thing again.
yeah,
But
okay.
it's the same thing. Like for example, you may have done this in quantum field theory, that when you write down say Klein-Gordon Lagrangian, okay, then when you write down Klein-Gordon Lagrangian, you get the free Klein-Gordon Lagrangian. Then you get a term which is some energy functional Ek times Ak dagger Ak plus Ak dagger, right?
Yeah.
And then what you did was that you said that like, no, I want to normal order this thing. And so therefore I replace AK dagger by AK dagger AK minus half or plus half or some such thing. This the harmonic oscillator
Yeah.
commutation relation will give you that factor. That factor of half is there for every k value. And you'll have to integrate over all k values, and that is a divergent number. Okay. But what we say is that like we don't care about that divergent number, because what we measure are the energy differences. Okay, and therefore on that divergent number you have a ground state and excited state, both of them carrying that divergent number plus some values. And the difference between these two energy levels is the only thing that is relevant, and therefore that number we don't care about. Okay, this argument is exactly that.
Yeah, I understand that we can arbitrarily add a constant or subtract it or whatever.
Yeah.
And I mean, it looks too trivial right now that phi equal constant solution. We like in order to study this, we didn't even have to write the action.
Oh, that is right. Yeah, it is true. We'll need the action later, but right now we didn't need it. Yeah. But like, forget about this, which may look like too ad hoc or stuff, this thing. But even in standard model, Higgs field has a constant vacuum expectation value, exactly this kind of number. Okay, and it is assumed to be constant everywhere in space-time.
Yeah, but this is the same sort of approximation that we did in mean field theory by justification that each spin site experiences a net magnetic field sort of a thing.
Exactly, exactly. So this is how this will produce mean field theory only.
Yeah, but we don't want that, no? Like.
But like at least we have a Lagrangian formulation of producing mean field theory. That earlier one was only an ad hoc statement, right? That you just said something by fiat. Here the Lagrangian tells you that these are the extrema, right? So you have an action principle which gives you a mean field theory. Of course, Landau-Ginsberg theory is not just doing mean field theory. There are of course improvements over that, which because of the Lagrangian formulation you are able to do that. In mean field theory, you have to kind of invent techniques of improvising over mean field theory.
Okay.
Okay. So let's kind of look at the critical exponents, and as Kaustuv kind of already guessed, we are going to essentially reproduce critical exponents of the mean field theory. Okay. So let's see how we get there. Okay. So we write down the Landau-Ginsberg partition function as e to the minus beta f, where f is the I need not have written beta actually. F is the minimum value of the action that we are looking at. Okay, and we know that that for t greater than tc, we have phi is equal to 0, grad phi is equal to 0, and therefore S minimum is trivially 0. Okay, for t less than tc, phi m would choose any one of these two values because this is not the minimum, this is a local maximum. So therefore, this is the minimum value that it picks up, and grad phi continues to be 0. Okay, so that is the setup. So you can ask what is the minimum value of the action. Okay, and that number you can just substitute the value of phi to be square root of minus a by g and compute. Okay, and as Kaustuv was saying, it would be kind of large value because it will be proportional to the volume of the space. So here's the number. Okay, we don't really care about this number simply because we are really interested in differences in energy, and this number is just going to sit around in every term. Okay, but nevertheless, the dependence of that on various quantities is important for us, and we want to look at that dependence. Okay, not about the large values that that it is taking. Okay, so if you are close to t equals tc, then on one side you get S minimum to be 0, t greater than tc. On the other side you get S minimum to have non-trivial value. Okay, so let's look at what that is. Okay, so this quantity can be written as the same value, okay, times tc minus t theta function. So this theta function says that if tc minus t is less than 0, then its value is 0. If tc minus t is greater than 0, then its value is 1. Okay, that is what this object is. Okay, we have a squared sitting around which depends on temperature, and therefore this quantity is proportional to t minus tc squared. Okay, so this is the kind of behavior that the minimum of the action would show. Okay, so what we can do is ask, how does the specific heat look like? Okay, so specific heat is a second derivative of the free energy, which is same as S minimum with respect to temperature. Okay, and compute that for t greater than tc, you would get one constant because this entire stuff would vanish. T less than tc, you will get another constant. Okay, and that is proportional to this fellow. Okay, so I should have said proportional because there are quantities sitting around some factors, but it's a constant value. Okay, so therefore CV both above TC and below TC seems to take constant value. Okay, and therefore the critical exponent would be 0, which is what the mean field value was. Okay, only thing is that which was also seen in mean field theory, that CV is actually discontinuous across the transition. It would, because S minimum was 0 for t greater than TC, CV would just vanish. Okay, whereas it would be some non-zero constant below TC. Okay. Fine. Now, the minimum value of phi, remember that is square root of a by g. Okay. So, minimum value of phi is proportional to square root of a. Okay. But remember, phi is the order parameter. So, in the Ising model, this would be magnetization. So, that would go as square root of a, but a goes as t minus tc. So, therefore, magnetization would go as t minus tc to the half. Okay, of course, you know, magnetization is non-zero below TC, so it will go as TC minus T to the half. Okay, and therefore you get beta equals half, which is precisely the mean field theory critical exponent. Okay. Now, if you want to determine the response to the external magnetic field, let's turn on the external magnetic field. Then you have H times phi term sitting in the action. And when you extremize the equation, then you get an inhomogeneous term because that this H couples to phi linearly, and equation of motion therefore would give you a term involving H, and this minimization equation would look like this. Okay. Now take this equation and suppose you are working at t is equal to Tc. Okay. If you are working at t is equal to Tc, then A would vanish because A is A0 times t minus Tc. So therefore, this term would vanish. Okay, and what you would get is that yeah. So maybe I should yeah. So maybe I'm doing something else right now. I'll come back to the other one later. But like suppose you are close to Tc. Okay, then phi m takes small value. You have say temperature is less than Tc but close to Tc. Then the order parameter takes small values. You can ignore the higher order term. Okay, and then you get phi m to be proportional to H. Okay, and therefore the susceptibility, which is the derivative of the magnetization with respect to the magnetic field, would be proportional to 1 over A. Okay, and that would mean that susceptibility goes as 1 over T minus Tc. Okay, and this tells you that the susceptibility exponent therefore would be 1. Okay, gamma equals 1 because that should go as T minus Tc to the minus gamma, and that tells you that gamma is 1. Okay. The next quantity that we can compute is the correlation functions. Okay, so compute say 2-point function for the scalar field, and so to do that, we'll have to study fluctuations around the extremum value of phi. So phi is equal to phi m is the minimum. We denote the fluctuation by var phi. Okay, and and we'll substitute that in the action. Okay, so here's the exercise for that. Okay, so take phi of x, which is the way kind of scalar field in the Landau-Ginsberg model. Okay, write phi of x as its extremal value phi m plus the fluctuation var phi x. Okay, and put it in the action of the Landau-Ginsberg model. Okay, and once you do that, then you would get some terms which are independent of phi. So you can ignore those. Okay, so you can try to figure out as to why you can ignore those. Okay, Then look at the terms which are linear in phi. Okay, you can set those terms to 0. Okay, so you can check that also as to why you would want to do that. Okay, and then you show that if you keep the terms which are there in the action after weeding out these two pieces, then your action would take the form like this. Okay, it's not a very difficult exercise. You need to figure out why you want to do this, but once you figure that out, this is kind of obvious. Okay, just straightforward substitution. Also, it is important to note that phi m is actually constant. Okay, is the configuration that we are looking at. Okay, so therefore it won't appear in the derivatives here. Okay, it does appear in the expressions here, but not in the derivative. Okay, so what we'll do is that we will look at the terms which are up to quadratic terms here. Okay, so that means we are going to ignore cubic and quartic pieces. So we can just pull those factors out. You have half grad phi squared, which is this piece, and a by 2 plus 3g by 2 times phi m squared. Okay, times the bar phi squared. Okay, so that is the quadratic part of the action that you will get for the fluctuation. Okay, so clearly, if you think of this as a fluctuation, and this field of course depends on the space, d-dimensional space, then you can think of this as a scalar field theory, and you can interpret this quantity as m squared by 2 factor. Okay, half grad phi squared plus m squared by 2 phi squared. Okay, so therefore you get an expression which is m squared by 2 is equal to a by 2 plus 3g by 2 times phi m squared. Okay, and you can see that this quantity when phi m is equal to 0 is just a by 2, and when phi m is not,
minus of that, right?
What is minus?
Like mass is negative
No,
of
no,
this.
no. This is a Euclidean energy functional, no? Right?
Oh, we have already done that thing. Oh. Okay.
No, we are working with Euclidean functional all the time. So therefore, grad square plus mass squared by 2. Okay.
Okay.
So yeah. So when phi m is equal to 0, you just get a by 2, which is this term. That's what happens when t is greater than tc. And when phi m is not equal to 0, which is square root, when phi m squared is minus a by g, then you can check that you get this quantity to be minus 3 by 2a, and plus half a will give you minus a. Okay, so that is for t less than tc. Okay, now this may again give you an impression that that mass squared becomes negative for t less than tc, but that's not true again. Okay, because when t is less than tc, then a itself is negative. Okay, so therefore since a is a naught into t minus tc, a by 2 is positive when t is greater than tc, and minus a is also positive when t is less than tc, because when t is less than tc, this quantity is negative, this minus sign is soaked up by this fellow. Okay, so in both cases, the m squared by 2 term is always positive. Okay, fine, and that is simply because in the first case you have a single minimum and particle has mass square root of a, and in this other case you have double minimum, and around any of those minima, and we are not expanding around a maximum, but we are expanding around minimum, around any of those two minima, the mass of the particle is square root 2 times a. Okay, so that is, so the mass actually enhances after you get into a double well problem. Okay, and that is related to what is the behavior of the harmonic oscillator around the minimum. Okay, so therefore this minus a does not really tell us that the mass squared is negative. Mass squared is in both cases positive. Okay, so here's another exercise that So suppose we write down a Fourier decomposition of phi of x as integral d dk upon 2 pi to the d times exponential I k dot x times phi tilde of k. Okay, this is a Fourier transform of this quantity, and substitute this into the action. Okay, and suppose you look at the quadratic part of the action, then you can check that after substituting this in the quadratic part of the action, the action for the fluctuation S var phi, okay, would be half times integral d dk upon 2 pi to the d times mod phi tilde k squared times k squared plus n squared. Okay, it's kind of a straightforward thing. You must have done something similar in scalar field theory in QFT1. Okay, if not, you can try doing it again here. Okay, now of course to do that you need to substitute each phi of x as this kind of Fourier transform. One of them will have k1, the other one will have k2 or something like that, or k prime, whatever you want to choose, and then you have to use this relation, that integral d dx, which is the integral which is defined in the original action functional, with e to the I k1 plus k2 dotted with x gives your d-dimensional delta function, which is 2 pi to the d. Okay, you can use this fact because you need to use this fact because when you do a substitution in the quadratic term, you have two integrals, ddk1, ddk2, and you need to get rid of one of the integral, which will be done by this delta function. Okay, so spatial integral is removed by this integral, which produces a delta function. There are two k integrals. One of them will be removed by this delta function. Okay, that is how you should be landing here. Okay, fine. Remember, the field phi was considered to be real. Okay, so therefore the reality condition implies that phi tilde of minus k must be complex conjugate of phi of k, phi tilde of k. Okay, so that would ensure that the field is that the field phi x is real. Okay, so is this fine?
Yeah.
Yeah. Okay. Fine. So there's one more exercise. This thing. So using this result of in the previous exercise, you can show that 2-point function for phi tilde k1 phi tilde k2 takes the form 2 pi to the d times d-dimensional delta function involving k1 plus k2. Okay, divided by k1 squared plus m squared. Okay. Now there are various ways of doing it. You must have done something similar in the quantum field theory 1 course, but you could also take the path integral approach to do this computation. And in that case, what you need to do is to do something where, yeah, I don't know whether I have written down all that stuff or not, but let's kind of roll back and check. Oh yeah, I don't think I have written all that. But anyway, so let's look at this expression. Okay, this or the Euclidean one, maybe that is safer. Okay, so suppose you look at this expression and your Euclidean action is the Landau-Ginsburg energy functional. Okay, but remember that the Landau-Ginsburg energy functional has the term which is grad phi square plus the potential term, which is a phi squared plus g phi to the 4 with some factors of half and a quarter and so on. Okay, now I don't know whether I can kind of quickly reach there. So imagine that your S Euclidean is something like this. Okay, this is the Landau-Ginsburg energy functional, and this is the additional term. Okay, now if you want to compute 2-point function, then one thing that you could do is differentiate this SE, which is this right hand side of this, differentiate SE with respect to H twice. Okay, fine. So ideally H should be sitting inside and should be a function of X, so that you can take derivative of H of X and H of 0 if you want to have a 2-point function with one field defined at X and another field defined at 0. Okay, but what you could do is that you can do that kind of stuff. If you differentiate it twice, then this phi of X1 and phi of X2 will come and sit below. Okay, so integral d phi of X1 phi of X2 exponential of e to the minus S, okay, is precisely the computation of correlation function. Okay, so of course, when you do that computation, you may want to set H to 0 at the end of this differentiation. Okay, then you get an expression sitting in the exponent, which is the expression that we have already derived, and from which you can compute the 2-point function. Okay. So this is the yeah. So looking at this action functional, you can derive the quadratic part of the action, which was that other exercise, right? This one. Okay. So now you can imagine that, like, your action functional is basically this term. Okay, and you have path integral integrated over d phi times phi of x1 times phi of x2 times exponential of this quantity. Okay, and you can try to determine how the double derivative with respect to h can be written in terms of inverse power of k squared plus m squared. Okay, that is basically this exercise, that you get this quantity. Okay, and the trick is the following: that imagine that your Euclidean action was this term plus h times h tilde times phi tilde. Okay, then when you take, I mean, I'm talking about h tilde times phi tilde because we are writing it in momentum space. Otherwise, you could have worked in real space also. That's not a problem. But we are doing it in momentum space. So take this term plus the source term, which is h tilde times phi tilde. When you differentiate with respect to h tilde twice, the phi tilde will come down, okay, in the path integral. But instead of doing that, what you could do is you have a term which is quadratic in phi multiplied by this quantity, and a term linear in phi multiplied by h. Okay, you can complete the square of this quantity, phi squared times something plus h times phi. You add a term which is like term proportional to h squared, so that you can complete the square. But when you add, you have to subtract that term also, right? So you add term h squared times something minus h squared times the same stuff. The first term plus the term linear in h phi plus and this term completes into a total square. That is a Gaussian integral which gives you a number. Okay. The term that survives is the term minus h squared term with something sandwiched in between. You can check with this factor that the term sandwiched between two h tildes is just inverse of k squared plus m squared. Okay. Now, as I told you some time ago, that computing 2-point function implies differentiating twice with respect to h. Now you have a h squared with k 1 over k squared plus m squared multiplying it. If you differentiate it twice with respect to h, 1 over k squared plus m squared will come down. Okay, and that is this. That is this expression. Okay, so computing this using path integral technique becomes almost triviality. It's very instructive to kind of do it once. Okay. Of of course, in quantum field theory 2 course, you will kind of study it much more rigorously. I did not do that because it would take like about 6-7 lectures to do everything rigorously. That would kind of almost derail the course. Okay, but you may want to kind of learn this technique of computing 2-point function. Doesn't matter whether in Fourier space or in real space, using path integral technique. Quite instructive. Okay. Now, of course, once you have computed this, you can do an inverse Fourier transform and compute the quantity in real space. Why do we want to compute it in real space? Because we have done this computation in real, I mean, not we, but people have done this computation in real space earlier. Okay, fine. But we know this quantity. This quantity for a free theory, or the quadratic part of the theory, is just 1 over k squared plus m squared with a delta function. The delta function is useful, gets rid of one of the integrals. Okay, and the other integral involves computing the Fourier transform of 1 over k squared plus m squared. Okay, what we want to do is not really compute this Fourier transform, but just determine what is the behavior of this quantity, or what is the dependence of this quantity on the mass parameter. Why are we interested in looking at mass parameter?
Because the mass term contains the temperature dependence.
Exactly. So we actually want to determine what is the temperature dependence of this quantity. That's why we just want to look at how it depends on the mass parameter. Okay. So so precisely for this reason, we will not actually evaluate the integral, but we'll just ask what is its temperature dependence. Okay. So best way to do that is to rescale the momentum as p times some other momentum, m times some other momentum p, okay, and plug it in. If you do that, then you get an integral which looks like this. Okay, there is a 1 over k squared plus m squared is replaced by p squared plus 1. There is an overall m squared factor coming down out, which is written as m to the minus 2. Okay, then there is a delta function factor here, but that is not important because delta function factor and one of the k integral will cancel each other. Okay, and the remaining k integral give you m to the d. Okay, so you get m to the d minus 2 times this integral. Okay, we really don't care what is the value of this integral, but we know that the 2-point correlation function goes as t minus tc to the d minus 2 by 2. Okay, right? Okay, so now what we want to do is we use this fact, okay, whatever is this function, okay, we want to write down the corresponding Fourier transform as a function of, remember this is a, sorry, I'm going back and forth for nothing. Okay, so once you write down, do this rescaling of momentum in this fashion, then k1 was a momentum which was, dimension full. But p is a momentum which is not a dimension full quantity because m already soaks up the dimension of the momentum. So p is a dimensionless momentum. Okay, so therefore you can kind of not worry about the dimension dependence of p at all. Whatever is a Fourier transform, that can therefore be written in terms of a dimensionless quantity in real space. That means it must be a function of mod x times the scale parameter, and the only scale parameter that is available with us is the mass, or T minus Tc, temperature. Okay, so what we are going to do is substitute this the Fourier transform by a function which is a function of mod x times m. Okay, but what we know is that this correlation function is a function of mod x by xi, where xi is a correlation length. Okay, so therefore xi should be proportional to 1 over m because that is the only scale available in our theory, and xi would have therefore picked up the dependence on the only scale that is available. Okay, since this is dependent on length and this is dependent on inverse length, their relation turns out is on numerical factor times 1 over m. Okay. We are not interested in numerical factors, but we are interested in how it behaves as a function of t minus tc. Since it depends on m, it will go as t minus tc to the half. Okay. And that's why our critical exponent nu would be half. Okay. Again, the mean field theory value. Okay. All this computation, of course, is done in the neighborhood of the critical point. But if you are really exactly at the critical point, then m is going to vanish. Why? Because m is proportional to t minus tc, or rather m square is proportional to t minus tc. So therefore, as t is equal to tc, the mass is going to vanish. Okay. So that would tell us that the the correlation length is going to diverge. Okay, exactly as t equals tc. Okay, fine. So if that is the case, then one could ask a question as to how would the two-point function behave. Now, try recalling how the two-point function was written. Two-point function was written by as mod x to the 2 minus d. The minus eta factor comes about only at t is equal to tc. Otherwise, it is written as mod x to the 2 minus d times exponential of some exponential of minus mod x by xi. Okay, that is the behavior of the two-point function, that it falls off exponentially and it has a power law term which goes like this. Okay, but if xi goes to infinity, then the exponential term just goes away. Okay, and only remnant of that we could get is that the correlation function may not fall off as mod x to the 2 minus d, but it may have some anomalous piece. So this is what is called the anomalous dimension of the operator. Okay. It turns out that, like in our case, the anomalous dimension would just turn out to be 0, because at t equals tc, that p squared plus 1 kind of term just becomes p squared. You can choose to go back to the original k variable, try to do a Fourier transform of this, you just get 1 over mod x to the d minus 2. Okay. So if you compare these two quantities, you just find eta is equal to 0. Okay, which is again the mean field theory value. Okay. So now all these quantities are in some sense, derivable by writing down a path integral for the lambda Ginsberg energy functional. Okay, fine. Okay, so the last thing that we want to look at is what happens when we are at t equals tc, and as I said just now and some time ago also, that at t is equal to tc, the mass is going to vanish, or the term a would vanish in the potential. And if you kind of want to determine the critical exponent delta, you turn on the magnetic field and look at how the magnetization depends on h. Okay, so at t equals tc, because the mass term vanishes, you get a equation which is g times phi m cube minus h is equal to 0. Okay, this was the equation that we had seen some time ago. Yeah, sorry, I may have missed it. Sorry, it looks like I kind of skipped over it. Okay, maybe we can forget about it right now. But what we had was a term which is like a plus phi plus g times phi cube minus h equals 0, and we said that very close to t equals tc, you can ignore phi cube term and say that phi was proportional to h by a, and said that the magnetization goes as t minus tc to the minus half. Okay, but now what we are doing is we are sitting right at t equals tc. That linear term goes away. Only cubic term is relevant, and it tells you that the magnetization or the order parameter goes as h to the 1/3, which tells you that delta is equal to 3, which is again the mean field value. Okay, so therefore what we see is that the Landau-Ginsberg model reproduces all the mean field theory critical exponents by using the axional function. Okay. Now, as we discussed, that we already know that the mean field theory exponents do not agree with the experiments. Okay. And most important problem with the mean field theory or Landau-Ginsberg exponents was that they are dimension independent. Okay, and therefore they are not consistent with the experimental results, because experimental results do depend on the dimension of the space in which you are studying the system. Okay, so we would want to ask a question as to what is, what is the validity of the mean field theory. Okay, so recall, I have to kind of get these pages look a little better. I mean, push this equation down and so on. I'll do that sentence down and so on. I'll do that later, but right now, let's work with this. So, so in mean field theory, remember we had claimed that that every spin interacts with the mean field generated by all other spins. Okay, that is what is the statement, that SI couples to the average value of Sj, and then there is a fluctuation. Okay, so of course, if you look at the term in the square bracket, that is same as Sj. Okay, but what we do is we treat the first term, Jij Si times average value of Sj, as the leading piece, and Jij Si times this difference from the average value as a fluctuation. Okay, and therefore in mean field theory, we say that this is the one which is going to give you the most dominant contribution. Okay, so so that is a kind of mean field theory proposal. We could ask a question that, like, that since it does not agree very well with the experiment, so is the mean field approximation valid? Okay, and so to get the estimate, one has to kind of get some parametric way of determining these quantities, define a criteria which will tell us whether the mean field approximation is reliable or not. Okay, so so what we will do is that we will kind of define a function which kind of computes the error between the exact value versus the mean field value. Okay, so this error function is written, not function, but this error is written like Eij is equal to the average value of Sij minus average Si times average Sj upon average Si times average Sj. That is the quantity. Okay. The upstairs is, of course, you are taking a modulus. You don't worry about the sign of it. You are just trying to figure out what is the deviation of the exact answer from whatever the mean field expression is. Okay. But if you look at the numerator, then you can realize that, like, this is a 2-point function of the two spin variables, right? Because remember, the 2-point function was defined as Si Sj expectation value minus the expectation value of Si times expectation value of Sj. This is what is referred to as the connected 2-point function. Okay. Otherwise, this could have disconnected part. Okay, but you subtract the disconnected part out. So the total term in the numerator is just the connected Green's function. Okay, a connected 2-point function. Okay, so this is kind of, on an average, this is kind of a difference between the two expressions. Okay. So this is something I was just saying, that the numerator is really the 2-point function, correlation function, and the denominator is basically just the square of the order parameter, right? Because average value of Si is the magnetization. Okay, so therefore mod of the 2-point function divided by square of the order parameter. So that is why we are going to write E as mod of G R, where R is a kind of modulus of distance between points, 2 points, divided by phi m squared. Phi m simply because we have decided that in Landau-Ginsburg model we are going to use phi to denote the order parameter. Okay, fine. So what we are going to say is that if the error is small, okay, then mean field theory is correct, okay, and self-consistent. By that one means that the 2-point function is small compared to the mean value of the order parameter. Okay, that means fluctuations. After all, 2-point function is related to fluctuations. Okay, so this statement tells you that the fluctuations around the mean field value are small compared to the magnitude of the mean field value itself. Okay, and therefore it may not destabilize the mean field solution. Okay, so if this is the situation, then you would say that your mean field theory is correct, or at least it is self-consistent. Okay, so of course it may still not give you the correct answers, but you could try to improvise over the mean field theory answer to so that you can arrive at the correct answer. Okay, so mean field theory is of course a very crude approximation. Even in the Landau-Ginsburg model, it's a crude approximation. You can improvise over that, provided the mean field theory criteria that we have written down is telling us that mean field theory is stable or is correct, so that you can kind of improvise over that. Okay. However, if it is not that way, if E is equal to 1 or if E is kind of greater than 1, then mean field theory is not reliable, and in that case fluctuations can destabilize the mean field. Okay, so this is how kind of we are going to look at the problem. So what we'll do in the next lecture is to look at this criteria and try to see under what circumstances can we kind of say that the mean field theory is a reliable method. Okay. So I'll stop here today. Any questions?
I mean, we already had an estimate, right? That mean field theory is not good.
Yeah. But we do not have a criteria. In fact, even this is not a good enough criteria. What we will do is we will develop what is called the Ginsberg criteria, which will be a better kind of way of deciding whether the mean field theory is good or not. See, whether the mean field theory is good or not has nothing to do with whether mean field theory gives you a right answer or not. The question is that is the mean field theory a good point about which you could kind of try to improvise your result to get correct answers. Okay, if there is no chance of having improvisation over mean field theory giving correct answers, if you are likely to go in the wrong direction, then you wouldn't even want to start with mean field theory. On the other hand, if you expect that the mean field theory is going to drive the results towards more self-consistent answers, then you would say that like, okay, mean field theory is a good starting point. Okay.
Yeah.
So in fact, after we establish the Ginsberg criteria, we will see that like there is Ginsberg criteria actually makes the whole story dimension dependent, and in fact tells you that there exists a critical dimension above which mean field theory is exact. Okay. It turns out that like for example, for Ising model, the critical dimension is 4. Okay. Remember, 4 is the spatial dimension really. Okay. So, but the interesting models that we would want to look at is 3-dimensional Ising model and at best a 4-dimensional Ising model. Okay. the mean field theory would be exact for dimensions above 4. Okay, so the Ginsberg criteria, in fact, would tell you that there exist critical dimensions above which mean field theory is going to make sense, below which you will have to study whether mean field theory is stable or not. If it is stable, then you can improvise over that. You can study techniques which will improvise results over mean field. If it is not stable, you just dump the idea, look at a completely different formulation. For example, and it's not like that you often find mean field theory being a very good starting point. It is not. In fact, for example, say systems like high TC superconductivity. If you try to kind of consider electrons as the right kind of variables, and from which you want to kind of form some kind of a bosonic degree of freedom, which kind of condenses, and after it condenses, there is a superconductivity. That is not correct, actually. In fact, the right kind of quasi particles are totally different, in fact, and they cannot be obtained in a very perturbative fashion. So, if the mean field theory cannot capture that new type of quasi particles in a simple way, okay, then kind of straightforward mean field theory with original set of variables is a wrong thing to do. Okay, but like somebody like Anderson almost 30 years ago showed that, like, instead of that, if you define new class of quasi particles where spin and charge degrees of freedom can separate and propagate differently, then you can explain several high TC phenomena, and this separation of spin and charge degrees of freedom, of course, cannot occur perturbatively. So therefore, it's a completely new kind of vacuum about which you are kind of trying to do mean field theory. So, or I shouldn't say mean field theory, about which you are studying quantum field theory. Okay, so so it is not like that every time you write down mean field theory and you find that it is stable. In fact, it's not the case. But it's also not the case that, like, that mean field theory gives the wrong answer and therefore it is always unstable. So it case by case it depends, and one has to take a call on that. So Ginsberg criteria is a criteria which tells you whether you want to kind of go ahead with mean field theory or not. Okay.
Yeah. Also, since you brought it up, like, do we write things like Lagrangian for quasi particles also?
Yeah, of course.
Then do we expect them to behave Lorentz algebra and all? Like,
well, okay. Okay, so let me not give you a condensed matter analogy, because in condensed matter physics you don't kind of care about Lorentz symmetry and stuff like that, right? I mean, they are never worried about relativistic invariance and so on. But let me give you a string theory answer, not answer, example. Okay, so for example, in string theory, I mean, you don't have to do string